So early on in the drive for innovation, I got an email from an EE Times reader, Lloyd Banta at Droplet Measurement Technologies, and he said, if you're in Denver during this trip, or Denver's environs, why don't you come by and check out Droplet? And so that's why we're here.
Here we are at Droplet Measurement Technologies, a small company of 20 or 30 employees that is in the business of making instruments for atmospheric research. Our core business is measuring the atmosphere under real atmospheric conditions, which means airplanes. A popular use of our products is in icing research for aircraft safety, and this picture and this picture show instruments being used for icing research or certification. China likes to buy a lot of our instruments for weather modification, cloud seeding. Our instruments can be used to determine if a cloud is worth seeding. Typically, that means you seed a cloud that's likely to produce rain. Another of our customers, for example, is Hydro Tasmania. Their task is to ensure that the reservoirs are full, so when they see a cloud coming, they go up and seed the clouds. One amusing side consequence of that is that whenever there's a rainstorm that drives away the tourists, and an airplane in the air at the same time, Hydro Tasmania gets angry letters from the tourism centers.
All right, Lloyd, what are we looking at here?
This is a cloud imaging probe. It's conceptually quite simple. There's a laser that shines a path, a flat beam of light across an aperture, and that is reflected into a diode array, and we measure shadows. And we measure the shadows of cloud particles. And the smallest cloud particle we measure is about 25 microns with this instrument. Other ones do 15 microns. But conceptually quite simple, but the fact is we're sampling at up to 25 megasamples as we fly through the clouds. Some of the airplanes that these go on fly nearly the speed of sound. And that's faster than any imaging, high-speed imaging camera can do, and it's also continuous. It's not flash, it's a continuous stream of pixels. This has a second instrument, which is rather interesting. It's called a liquid water content sensor, and it consists of a simple little piece of copper that's heated up to 125 degrees centigrade, and by measuring the power it dissipates, we can know how much liquid water is in the air. That's very important for icing, because if there's liquid water in the air and the temperature is below freezing, then there's the potential for ice forming on the airframe and causing the airplane to crash. It still happens. Similar measurement, completely different technology. This is a cloud droplet probe. It also has a laser, and it shines a relatively narrow beam across the aperture, and then we throw the entire beam away. It goes into a dump spot, it's called, and we measure only the scattered light. So this measures much smaller particles. This can measure particles as small as 2 microns up to about 30 microns in diameter. This is a variation on the forward scattering probe. It has a very bright laser, a 1-watt laser, and it has 2 sensors, an avalanche photodiode for measuring small particles and a PIN photodiode for measuring larger particles. And it can measure particles as small as 1/10 of a micron in diameter. Those would typically not be water particles. Those would be dust. This instrument is obviously a benchtop instrument. It won't fly in a cloud, but you'll see them in airplanes anyway. There'll be a probe sticking outside of the airplane that will sample the air. This instrument is designed to measure black carbon and its variance in the atmosphere. This is our latest instrument. It's called a photoacoustic extensiometer, and it makes 2 simultaneous measurements of an ensemble of particles. So all of our other instruments that I described measure 1 particle at a time. This measures an ensemble. This stainless steel tube that you see has a resonant frequency at normal atmospheric conditions of about 1500 hertz. We actually flashed a laser at the resonant frequency of the tube, and there's a microphone that would sit in here. And if the particles in the air absorb the laser light, they heat up and cool down at the frequency of the resonance, and we can measure an acoustic signal and determine how much absorbing particle there is in the air.
Lloyd, given this array of measurement instruments here that you've shown us, and it's kind of dizzying, the technology behind it, what's the biggest design engineering challenges you guys face today?
It's really interesting. I used to work in a business where saving a nickel was worth a few hours of work, and this is exactly the opposite. I can spend tens of dollars to save a few days of development time. We very often, we're selling state-of-the-art instruments, very small volume, so the really important questions are simply performance and time to market. You could call it time to market. It's actually, oftentimes our first instruments has a customer before we even start building it. So working with the customer, getting an instrument that makes the measurements that they need to make is the interesting challenge.